structures, molecules, Mr. Nicol, take one.
Okay, so we've just learned that Lewis structures will tell us about the valence electrons of an atom. So they show us which electrons they can contribute to a compound or a molecule. What we're going to look at now is just molecules. In the previous video you saw how an ionic compound can be represented. Lewis structures don't really work too well for those. What they're really powerful for is understanding where the electrons in a molecule come from. Now, one of the key things I want to say here is that all of those valence electrons contribute to the chemical bonds. So it's not that, for example, in an oxygen, 2 of them come from one oxygen and 2 come from the other to make the double bond. It's actually that 6 come from one oxygen and 6 come from the other to create an electron cloud that includes the chemical bond that has got, quickly do the maths, 12 electrons in it. Okay? So just be aware of that. Sometimes you're going to say, but hang on, those electrons have all come from that sulfur atom, for example. How come it makes a chemical bond? What's happening is all of the electrons, all of the valence electrons from all of the atoms are contributing to the entire electron cloud of the molecule, including its chemical bonds. Okay? So we use Lewis structures for molecules to show the bonding, the covalent bonds inside the molecules, the intramolecular bonding. Now, from this, we might be able to infer and work out the shape of the molecule, and then from that, we can work out if it's a polar molecule or not by using electronegativities and all those other tools that we've used so far. So we're getting really close to being at a stage of understanding polarity of molecules here. I'm going to use water as my example. So water is H2O. Now, one of the first things that I would suggest doing while you're learning to do this is to draw the atoms next to the formula. Okay, so I've got a hydrogen with its 1 valence electron. I've got another hydrogen with its 1 valence electron. And oxygen is number 8, so it has 2 in its first shell and 6 in its second shell. So it has got 1, 2, 3, 4, 5, 6 electrons in its valence shell, or energy level. The total number of electrons is really, really important. So the next thing I'm going to do is add up the total number of electrons. Valence electrons, sorry, I should be clear on that. So I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. At the very end, if I have more or less, that's poorly phrased, if I have fewer or more than 8 electrons, then I've done something wrong. And I'll show you this in another molecule later. This is a nice easy one that works. Then I look at how I think it might go together, a bit like a jigsaw puzzle. Well, I can see that there's a gap here, and there's a gap here. My aim is to have 8 electrons around every atom. There are a couple of exceptions. Hydrogen only needs 2 to fill its outer shell. Boron, which is also not a sort of semi-metal, boron only needs 6. It's an exception to the rule. So the 2 really big exceptions are hydrogen, 2 electrons, boron, 6. Other than that, we're trying to get 8 around every atom. So I can get 8 around that oxygen quite easily. They can share the 1 of each hydrogen to give hydrogen the 2 and to give oxygen its 8. What we call the octet rule. So I'm going to draw it again. I'm going to use a couple of colours so you can see where those electrons are coming from. So I'll just copy my oxygen in exactly as I had it before, and then put my hydrogens in like that. And that's what a Lewis diagram of water would look like. And you'll see some people will put the hydrogen there, some put it there. It doesn't matter, because all of those 8 electrons contribute to the chemical bond. So it's not important where you put the hydrogen. I like doing it this way though, because it's more close, it's more similar to the actual shape of the molecule. But you'll find that out at a later date. Now another way I can draw this, which is a little bit easier, is to go this way. I can replace any paired electrons between atoms with a line, which represents my covalent bond. But the thing I have to remember if I'm going to do that is I still have to include these other lone pairs of electrons. So ones that aren't bound to anything are called lone pairs of electrons. So that's showing 2, 4, 6, 8 electrons around oxygen. Fantastic. That obeys the octet rule. It's showing 2 electrons around hydrogen, which is great because that's all that hydrogen needs to be stable. So that is our Lewis diagram for water. Nice and simply done. Now I'm going to look at a different one that's a little bit harder. We're going to look at sulfur dioxide, SO2. Now, sulfur and oxygen both have got 6 valence electrons. Okay? So they all look basically the same. I'm sorry I'm getting cross, it's just a little bit quicker on the whiteboard. Okay, so that is 6, 12, 18 electrons. So it's a much harder one to start with. I'm going to start by putting the sulfur in the middle for the only reason that it's the first atom named here. Okay? I'm going to infer, and guess, that each oxygen is bound to sulfur. So it doesn't go sulfur, then oxygen, then oxygen. Okay? It's a pretty fair assumption to make, and again, experience will get you this one. So I'm going to put the sulfur in the middle, and I'm not going to put its electrons in yet. I've inferred that it's going to be bound to each oxygen, so why don't I just draw those chemical bonds in? And I'll just put mine aside, because it's nice and easy. This is the hard one, so I'm showing you another way to make it. The harder one, this is a big process. So I've drawn the chemical bonds. How many of my 18 electrons have I used so far? Well, each bond, I've said before, is worth 2, so I've used up 4. So we're down to needing to find somewhere to put 14 electrons. Now you can see why I've got the little tally over here. I'm down to needing 14. Okay, well look, the first thing I could do is just chuck a whole lot of electrons in. Make all of them obey the octet rule. Okay, 8 around that one. These are shared, remember? 8 around that one, 8 around that one, 8 around that one. Cool, finished, done. Who can see the problem? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons in the whole thing. 2 too many. Alright, so why don't I just get rid of 2? Okay, that could fix my problem. But it doesn't, because now this oxygen doesn't obey the octet rule. If you ever find this to be the case, what you do is you actually get rid of 4 electrons. 1 from each of 2 atoms that are neighbouring. Okay? And then what you do is you replace them with a double bond. Clearly, if I had to have 2 electrons be spread over 2 atoms, I'll have to share. So I put in a double bond. So to do it like the water above, this is what this would look like. I'll do sulfur in green. Hopefully you'll be able to see that with each colour I use and hopefully you can see that every single one of those atoms has contributed 6 electrons. I'm using the colours. However, it looks like sulfur has created this bond with oxygen all on its own. But remember what I said at the start. All of these electrons, all 18 of them, are involved in creating the chemical bonds and creating the overall electron cloud. So that's why it doesn't matter that it looks like sulfur contributed those. It could actually be that that one's a black one and that one there is a green one, because the electrons move around, so they don't just stay in that one place. So actually it doesn't matter where they've come from originally. So long as my electron cloud has 18 and every atom in there has got 8 electrons around it. Okay, because remember, that's the original thing about Lewis structures. They show the valence shell, or the valence electron. You want 8 in there for stability. Sulfur dioxide's one of the hardest ones you get, to be honest. They're not too hard at level 2. They do get a lot harder at level 3. I'm sorry to warn you about that. Either of these diagrams would be correct. So both of them are correct for sulfur dioxide. Just for your information, if I put sulfur trioxide, all you have to do is chuck the other the other oxygen on top here, and it works. So sulfur trioxide sometimes a trick when they give you, and it's actually just as easy as this one. Stop there.